Oh, here we go. Let's jump into a very cool video on how we can relate position and velocity in our continued quest to understand the basics of calculus in just a few short videos. So, video number 2 in lesson 1, let's go. So it says we will define the following variables. Velocity is v, or v of t, and s of t is the position, which would be where you are. Again, a reminder, velocity is how fast you're traveling and in what direction. So v could also be written v of t. So as I state here, an essential question of calculus is, how are velocity and position related with respect to time? Meaning, as time goes on, how does the rate at which something travels, how fast something travels, relate with the position, where you are as you travel? So as a car travels at a certain speed, where is it on the road? Okay, so we're going to look at this graphically, and then we're going to actually calculate some position graphs and velocity graphs. It'll be pretty rad. So this says v of t, meters per second, is our y value. And here we've got t equals seconds on the x-axis. Now, if we're looking at this, we will see that we've got, well, something that has 45 meters per second and traveling at like a nice constant rate. So let's just kind of take a quick look at this and see what this means and how it relates to its position graph. So pretend it's like a car or maybe an object moving at 45 meters per second. So if we take a look at this, notice that the area of this shape right here would be, well, let's think about it. It's a rectangle, so this would be 45 times 4. 4 is the width, 45 is the height of that graph, and 45 times 4 is equal to, curious, 180 meters. And you might be like, why is it meters? Well, we took 45 meters and we multiplied that 45 meters per second, and we multiplied that by 4 seconds. The seconds canceled and we were left with our units of meters. So 180 meters. Interesting. Well, didn't we just do the rate, 45 meters per second times the time? Or d equals rt. So the 180 meters is our displacement, which is the change in our position, where we are, or in this case, since we're traveling in one direction, the distance we traveled. Interesting. Well, now let's take a look at the position graph. As time goes on over 4 seconds, we travel 180 meters. Interesting indeed. Well, if we take a look at this, let's now look at it in a slightly different way. Let's look at the slope of this line. Well, this would be a change or a run of 4 and a rise of 180. And we know that slope, of course, is rise over run. Or if we take distance equals rate times time, we instead do distance divided by the time. And that will give us the rate. Well, the distance is 180 meters. Again, that's measured in meters. That's how far we've traveled, divided by the amount of time, 4 seconds. And that will give us 45 meters per second. Nice. So what we're basically showing here is this is the graph of where we are, the position. So our y values represent where we are at any time. Whereas here our y value represents how fast we're traveling and in what direction at any time. If you calculate the area between t equals 0 and t equals 4, we end up doing rate times time. The rate is the y value times the x value is time, and that gives us the displacement. Huge idea. So area is the displacement, how far we've traveled from time t equals 0 to time t equals 4. Again, displacement is not always how far you travel. In this case, it is because we're going in one direction. More on that down the road in this course. And then here, our slope ends up equaling that rate, because this right here is the position curve for this velocity curve. Sick. So the slope of this gives us the y value here, and the area here gives us the overall change in the y value there. Big ideas. Again, it's all distance equals rate times time. Okay, so let's keep flying. On to the next bit. We're told that we're given the graph of velocity. We want to sketch the graph of its corresponding position function. Well, let's see how that's done. First things first, I want to do this in a calculus way. So here's how I want you to do it specifically. Well, we know that we're going to get the position function. So that's s of t. And we know that this is the amount of time, seconds. So this is time in seconds. All right. So now from here, what am I going to do? Well, I'm going to calculate the area of each of these rectangles. And each of those rectangles will give me the amount of position that has changed. Because again, rate, this is the velocity right here, times the amount of time gives you displacement. So that's what we're doing here. Distance equals rate times time. So let's take a look here. This goes from 0 to 1. Well, that's going to be a width of 1. And this is a height of negative 40. That negative matters. It means that we're going, if we're going right and left, it means we're going to the left in the negative direction. So what's the area here? Rate times time is negative 40 times 1, which is negative 40. Sweet. Okay, well, what does that mean? Well, that means that over a time of 1 second, we will have traveled to the left 40 meters. So let's put 40 down here just randomly. And so I know that I'm going to travel in a nice straight line to that point right there. It's beautiful. And then at time t equals 1 to 2.5, we're going to travel for 40 meters per second that whole time. So that's a time change of 2.5 minus 1, or 1.5 seconds. And then the whole height the whole time is 40. So if I do rate times time would be the velocity times the time. I'm finding the area, yet again, between this graph and the x-axis. Cool stuff. 40 times 1.5, rate times time, is equal to 60. And that would be in meters, because you're doing meters per second times seconds. So you end up with meters. Nice. Well, what does that mean? Well, that means from time t equals 1 to time t equals 2.5, we will travel a total of 60 meters in the positive direction, because we have gained displacement here. We've gained position since we're going in the positive direction. And so that's going to end up going up 40 and then eventually up to 20. Boom. And there's your graph. And it makes a lot of sense. The slope of this graph is 60 over 1.5, which is, again, 40, positive 40. And the slope of this graph is going to be 40, right? Negative 40 down 40 over 1. It all matches up. Beautiful stuff. So that's how we can go from velocity to position. Very simply, find the area, and that gives you the displacement. Another big idea there, if you will, take a look at this graph. If we take the position graph at, let's say, s of 2.5, just to notice this, it's a big deal, minus s of 0, that would be the overall change in position, right? My end minus my start equals my overall change. Well, this would be an ending position of 20 meters, wherever that is. And we subtract from that our starting position, which is 0. So overall, we end up with 20. Now, who's to say that we started at 0? We don't know if we did. Had we started at, let's say, negative 20, we still would have gone down 40 and then up 60, and our change in position still would have been 20. So we don't know where we start. That doesn't change how far you've traveled. If you start at mile marker 5 and travel 80 miles, versus starting at mile marker 0 and travel 80 miles, you've still traveled 80 miles. That's still your displacement. Now, if we take our areas and we add them together, negative 40 plus 60, that's going to equal up to, well, 20. So again, adding each individual area, basically going backwards 40 and then forward 60 will give you your overall displacement. That's beautiful. So the area is the displacement, right? The overall change in position, or end minus start. That's going to be huge down the road. Okay, on to one more. We're going to go in reverse now. We're going to go from position back to a velocity graph. Well, this one's not as bad. This is more what you're used to from Algebra 1. So what we're going to do is we're going to notice that the y values on the velocity graph would be the slopes of position, because velocity is how fast our position is changing as time goes on, or in other words, the slope or the rate of change. So if we take a look at this, let's find our first slope. Well, we're going to do rise over run. So the run is 2, the rise is 60. So if we do 60 over 2, that gives us 30. And again, that's still just distance divided by time equals the overall rate, or displacement, I should say. And that gives me a value of 30. So my velocity is going to be at 30. So I'll just put like a random 30 here. These graphs are not perfect. And we're going to travel at a nice constant pace of 30, right to there. Technically, there's like an open circle there. Because at this point now, what is our slope? Well, our rise is 0, our run is 2. 4 minus 2. So our slope is 0. Well, that means that the y value I have on this graph, this would be the time in seconds, our y value on this graph is 0 because our velocity is 0. Let me do that in maybe a different color. I put an open circle here because technically at this point, I don't know what the slope is. And so I'm going to just draw this nice horizontal line because again, the y value in this graph is the slope from this graph because the velocity here is the slope and the velocity here is the y value. One last one, let's do it. So now we're being told that we have a slope of, well, let's see, we go down 60 and over 2. So that would be negative 60 over 2, which is equal to negative 30. So again, I'm going to put a nice little line down there at negative 30. The entire time we have a slope of negative 30. And I'll put a nice horizontal line there. And that's it, peeps. That's how we go from velocity to position graphs and position to velocity graphs. It's all about area and slope. Rad. Everything's dirt. I'm going to keep saying it. Distance equals rate times time.